So in this video, we're going to talk about the cylindrical shells and the idea of finding the volume. And it's just a different way of finding the volume. And essentially, if we look at a graph, just a simple cylindrical shell function, then we know that right here is the f of x. And essentially what we do is walk a distance of x. And then we have our limits of integration. So this is x. So we walk a distance of x, and then we have our limits of integration. Now, the careful thing about cylindrical shells that we need to realize is that if I rotate about y, I integrate with respect to x. Okay, vice versa, the opposite is true. If I rotate around x, I integrate with respect to y. So it's the opposite. So that's the big thing about cylindrical shells. Now, for cylindrical shells, there's a formula. So the volume is given by an integral from a to b of 2 pi x, which we just talked about. So that's given by 2 pi x f of x dx. And the opposite is true for the y, for integrating with respect to y. Now, this f of x, it doesn't change. And this we always say is always the upper function, yeah, minus the lower function. Okay. In this case, we're integrating with respect to x, so that's why I write f of x. But just keep that in mind. Okay, so let's look at the problem. So I have this problem here. It says find the volume of the solid generated by the regions where y is equal to the square root of x. X is equal to 1 and x is equal to 4 about the x-axis. So we know that we're rotating around the x-axis, so therefore integration must be in terms of we're rotating around the y-axis, so we know integration must be in terms of x. It's always the opposite. And so for this one, it's a bit simple. We're already given the limits of integration, and we're given a function. So this now becomes the integral from 1 to 4 of 2 pi x. Well, what's my function? F of x. Well, that just happen to be the square root of x dx. Okay, since 2 pi is a constant, I could go ahead and factor it out. So this becomes 2 pi from 1 to 4. So this becomes x times x to the 1/2. Okay, dx. This is x to the 1. I have the same basis, so I could go ahead and add my exponent. So this becomes 2 pi from 1 to 4 of x to the 3/2. And I still have my dx here. Okay. Now, what's my integral? Well, again, I have 2 pi on the outside. Okay. Well, if I add 1 to 3 halves, I get 5 halves. So this is x to the 5 halves. And then I just simply multiply by the reciprocal. So this becomes 2/5. Okay. And this will be all integrated from 1 to 4. Okay. So then it just simply becomes a matter of plugging in. So if I look at this, well, I have 2 pi out here, and that's factored out. And this becomes 2/5. This becomes 2/5, 4 to the 5 halves, minus 2/5, 1 to the 5 halves. Okay, and 2 pi is all being multiplied by that. Okay, so if I look at this, when I simplify, this now becomes 2 pi times, well, this will simplify to 64/5, and 1 2 times one to the any power is just 1, well, except from 0, but 1 to the n power is just 1. 1 to the 5/5 power is just 1. So this becomes 2 to the 5th times 1, which becomes 2 to the 5th. Okay. And if I look at this, if I subtract that, that becomes 2 pi times, well, 2 minus 64 is just 62. So this becomes 62/5. Okay. And again, we could simplify more. Okay. So we could say, okay, well, 2 times 62, that happens to be 124 pi/5. So that would be your volume there. Okay, so let's look at another one. So if I take a look at this one again, we're going to find the volume of the solid generated by the regions y is equal to x squared and y is equal to x about the x-axis. Okay, about the y-axis. So we know we got to integrate with respect to x. For this one, we got to find the limits of integration first. So we could just simply set the two functions equal to each other. And so this becomes x squared minus x is equal to 0, where I could factor out an x. Yeah, so this becomes x is equal to 0 and x is equal to 1. So therefore, my volume is given from 0 to 1 of 2 pi x. Well, what's my f of x? It's always the upper function minus the lower function. And so if I'm integrating with respect to x and I'm walking along the x-axis, well, I did not draw a graph here, okay? But, okay, so let's simply draw the graph. So here's y is equal to x squared, and here's y is equal to x. Yeah. Yeah. So we know that upper function will be given by y is equal to x, but I did not have to draw the graph. Yeah. Because I could just simply take any number between the limits of integration and plug in it for the function. And so if I do that, if I use 1/2, well, 1/2 squared is just 1/2 squared is just 1/4. Okay. And then I plug in 1/2 here is just 1/2. 1/2 is always bigger than 1/4. So we know that x is going to be the upper function minus x squared dx. Well, again, 2 pi is just a constant, so I could factor that out. So this becomes x times x minus x squared dx. Yeah, I could factor in I could multiply and distribute across. So this becomes 2 pi times from 0 to 1 of x squared minus x cubed dx. Okay, now the integration becomes very easy from there. Okay, we know this is 2 pi multiplied by x squared, x cubed over 3 minus x to the 4th over 4. Okay, and this is all integrated from 0 to 1. Now this simply becomes a matter of plugging in. So if I plug in, this becomes 2 pi times, well, this is 1 to the cube over 3 minus 1 to the 4th over 4. Okay. Let's put this in parentheses, and this is all being subtracted from, well, 0 cubed over 3 minus 0 4th over 4. Okay, and we know this will eventually go to 0. All this will eventually go to 0. So we only left with this part. And so if I'm looking at this, if I take so this will be simplified to 2 pi times 1/3 minus 1/4. Okay, well, we know 1/3 minus 1/4 is just 1/12. So this is 2 pi times 1 over 12. And again, we could simplify this becomes 1, this becomes 6. So our answer is just pi over 6.